Okay, so we often when we talk about reactions, so in grade 10, we do balancing, and all you have to do is say single, double, displacement, or whatever. And then in grade 11, we show you the activity series. So some single displacement reactions won't work. We show you the solubility table. You have to form a solid. Some reactions don't work. So far in thermochemistry, we really have focused on the first law of thermodynamics, that energy cannot be created or destroyed. And while that's obviously a very important law, there is other things going on with the reaction that are not as big, drastic of an issue as enthalpy change. However, it does affect whether a reaction is going to proceed without outside assistance or be spontaneous. So why do endothermic reactions happen naturally all the time? Why, if a reaction has to absorb energy, wouldn't that mean that it wouldn't occur? So there has to be more going on. And so the spontaneity in the universe is, or deals with, or is explained with the second and third law of thermodynamics. You may have talked about entropy in biology. So there is a significant amount of chaos and randomness that the biological world needs, or everything would just sort of be boring and status quo. You wouldn't have mutations that are advantageous and all that kind of thing. So far all we've done is said whether something is endo or exothermic, and so all we've considered is the energy, thermal energy, or the heat lost or gained. But now we're going to take into account when will a reaction be spontaneous. So quite a few of the questions you have to do are taking a look at, is there an increase in randomness or disorder or messiness in a reaction, or is there a decrease? And the last question, I think, for the homework is looking at an actual calculation. Okay? So a spontaneous reaction is a reaction that has enough energy to overcome activation energy and results in an energy release. But so far, we've really focused on reactions that release or absorb energy in terms of heat, but that doesn't always have to be the case. When a reaction is going to produce free energy or energy that is available to do work, then it's going to be considered spontaneous. So we'll talk about Gibbs free energy as well. And Gibbs is actually a physicist. So again, depending on how far you took your discussion of energy in physics, then maybe you mentioned him as well. So the energy available to do work and power, that's a big part of physics. So then a non-spontaneous reaction can only proceed with continuous outside assistance. And how do we figure that out? We are going to consider the change in entropy, which is the symbol delta S. So if you happen to do the 5.5 homework, there was a column for delta HF and a column for S values. So S is considering the change in entropy. So we're going to do a calculation very similar to the the one we did for 5.5, looking at adding the product values, their S values or entropy values, and then subtracting that from, or subtracting the reactants from that value. So there are good things about this. The reaction or the formula for delta S is almost identical to delta H, products minus reactants. You have to multiply by the coefficients, just like we did in 5.5. And the big difference here is that when you think of exothermic versus endothermic, exothermic, we say energy is released. Endothermic energy has to be absorbed, which is positive. Here, when something has a positive entropy, then that actually is sort of counterintuitive to that thinking of enthalpy change. Positive or an increase in entropy means that the reaction is more disordered or more spontaneous, and a decrease or negative will be less spontaneous. So what I've tried to do as we go through this is give summary points as much as possible, okay? So there are questions before number 10 and 11, which aren't calculation. They're asking you to look at a reaction or a process. One of the questions, I think it maybe is on the review, talks about a skier going down the hill. Where is disorder increasing or is disorder decreasing? So if somebody's standing at the top of the hill getting ready to ski, as they go down, could they hit a tree? Could they go left? Could they go right? The chance of chaos is increasing. It could be crazy. You have no idea what's going to happen, and that means that the entropy is increasing. So when you have a reaction, we want particles to react. In order to react, they have to come together or collide. So the greater the randomness, then the greater the chance that they are going to collide. So what we'll look at is some conditions for reaction. So if you have a solid is very boring. If you're changing from a solid state to a gaseous state, let's say, gases are moving all around, very crazy, then the spontaneity or the entropy is going to increase. The disorder is increasing. So even something like that, okay? So there are plenty of questions to practice, but it really seems kind of weird when we first talk about it, but it does make a lot of common sense too. Okay, so entropy is a measure, like a numerical value for the randomness or disorder of a system. So we are going to use the reference values. So again, that was just an extra column in the chart we've used before. So when you get to the calculation question, your textbook will want you to go look up those values in the book, okay? And entropy increases when disorder increases. So the messier a process is, the more possibilities of particles colliding and reacting. And that makes sense. So like I said, this looks virtually identical to what we did in 5.5. So this is the symbol for sum or add. So you have to add the values for the products minus the values once you've added them together for the reactants. You have to multiply by the coefficient, just like we did on Monday. So if you are asked more of a theoretical question, then you have to be, usually if it's a reaction, like something, arrow, something else, then you'll be given the states. So does it start as a solid? Does it start as a gas? What is it changing to? When you have all gases, you can count the number of moles based on the coefficients. So there's a variety of different ways you can look at the questions. So when you take a look at the homework, it's actually not very long. It doesn't take a very long time, but it's good because it gives you a whole bunch of different scenarios. So one of them will be looking at the states. One of the questions will be counting the moles of gas, that sort of thing. Okay, so when the entropy increases, then it's going to be greater, the entropy of the products, which means a move towards more disorder, which is what we want. So this, again, is a little bit different than what our thinking has been for enthalpy. A positive delta S is really the condition you're looking for. That means spontaneous. If you do not love alligator signs, then you can write positive and negative. Okay, so when the entropy is going to decrease, or the entropy of the products, it's becoming more organized, it's less crazy, less disordered, then it's going to be a negative delta S and non-spontaneous. Ooh. In general, in grade 11 and in grade 12, we sort of tried to move towards quantitative analysis. So you can definitely do that calculation. We are going to do calculations, but because this is the first time we've talked about entropy, there are theoretical questions as well. So if you are asked, is the value or is the reaction going to have an increase in entropy or decrease, and you have to give a reason, then you can talk about decrease in entropy, decrease in randomness is more organized. You can talk about we're going to look at 5 things in the next 2 slides that you can use for your reason. So there's a variety of answers. Okay, so actually if it printed like this, you can even put a giant box around both the bottom ones. Because this is going to help you answer those theoretical questions. So a system is going to experience an increase in entropy. So again, you can say greater than 0. You can say positive. That's the same thing. I'll accept either answer. So you can, if the question talks about if you have gases and there is more space to fill up, a greater volume, then the gases will be able to be a little bit more crazy. Temperature of the system increases. And this is a really, really common question. The physical state of a system is changing. So it'd be solid on the reactant side, and then liquid or gas or aqueous. Ions are more random, right? On the product side, or it says liquid to gas. And then if it was the other way, it would be negative or a decrease in entropy. Okay, and then let's do the same thing for this one. Be better than me. What the heck is going on here? Okay, so these are other conditions to have an increase in entropy. So again, greater than 0, positive is the same thing. So this one, this is, again, sort of a good way to quantitatively figure this out, but it has to be for gases. So what you can do is look at the coefficients in the reactants compared to the coefficients in the product. So, but again, it's sort of moving towards more randomness. So the moles, the coefficients of the reactants are less than the moles of the product. So you just have to count the coefficients. Complex molecules are broken down into simpler compounds or elements, sort of like decomposition reaction. And then this is still a physical change of state. But I don't know why it says it twice, but it is actually the most common type of question. Solid to start, and then a more random product. Okay, actually, let's just take a look here. Okay, so let's say you have hydrogen gas and oxygen gas. Are going to make water gas. I think this is really the trickiest type of example because it's all the same state. So how do we know what to do? So then this one is a little bit rare because you have to check for gases only. And so gas, 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 we're good. And then all you have to do is count or add up the coefficients. So on the reactant side, we have 2 plus 1. And on the product side, we have 2. Okay? And then you just have to decide, are the moles of reactants greater or less than the moles of product? They are greater, so that means that it's becoming more ordered and less random. You could also think of this one as well. It's actually becoming a more complex molecule, which means a decrease in entropy. If this was the other way around, then it would be decomposing or breaking apart into more random compounds. So again, when you do the theoretical questions, there is a variety of answers, okay? Sometimes. Okay, so the moles of reactants are greater than the moles of product. Entropy decreases. Delta S is less than 0 or negative. All of those are equivalent. Okay? So when I made the solutions for the homework, I think I tried to do different questions differently. So sometimes I wrote positive and negative. Sometimes I did the delta S greater than or less than 0. So hopefully you can just, have a different use your own strategy when you have to do the theoretical questions. If you're given numbers, then that's great. That's easier to do. Like if you calculate delta S, so when you do the first few questions for homework, these 2 slides are the ones you're going to need, okay? And like I said, the physical state, solid to liquid or gas, or aqueous to solid, that's going to be the most common type of question. Okay, so how do we take into account both the delta H and the delta S value? So like I said, the physicist, he was a physicist, Gibbs. So if you were in physics and Mr. Devine talked a lot about energy, then he may have mentioned Gibbs free energy. So he discovered a relationship between energy change, entropy change, and temperature. And when we do these calculations, we're going to include the temperature, but we're going to use the standard value, which is room temperature, or 25 degrees Celsius. As you know from grade 11, when we did gases especially, when you change the temperature of something, then things can be very different. Gases start to move faster. They can take up more space. If I asked you to dissolve a solid in water that wasn't dissolving, one of the first things you would probably do is warm up the water. So temperature has a really big impact on a reaction. So when we do these calculations, we're actually going to stick with 25 degrees Celsius or 298 Kelvin. So that's good. The temperature value will always be the same. And then the delta H, you calculate like we did on Monday, and the delta S, you also have to calculate. So when you look at number 11, especially in the homework, you'll see that The questions sort of take up quite a few calculations. So obviously I can't ask you, 4 or 5 of these because they just take up too much time. So delta G, or the Gibbs free energy, is the best indication for whether a reaction is going to proceed spontaneously or not. If you are going to take the AP exam, they call it thermodynamically favored, which also makes a lot of sense. So yes, we often think of heat transfer. That's easy for us to measure, but not every reaction will do that. So Gibbs free energy is a much more universal measure of whether a reaction is spontaneous or not. So should you continue in, sciences, for science students like physics, chemistry, biochemistry, not necessarily, life sciences and healthcare, then you'll yes, you might talk a little bit about enthalpy, but you'll probably talk way more about Gibbs free energy. It is the best way to give an indication about whether a reaction is favorable or not. And the good news is Gibbs free energy makes sense because we've been doing so much exo and endothermic. So let's highlight this formula. And this down here. Okay, so when delta G is negative, which is what you would sort of think with exothermic, so when the delta H value has a greater negative value, so it's exothermic, then the change is spontaneous. When the delta G is positive, we say the change is non-spontaneous. So what we're going to do when you calculate delta H and delta S, you have to multiply by the coefficients, which means that it cancels out the moles. So Gibbs free energy is kilojoules, but you can do dimensional analysis to figure that out. I don't know why I didn't write KJ there. So enthalpy change also has to be kilojoules, and then temperature will be in Kelvin. But again, we're going to use a standard value because we're using the standard delta H and S values. And then entropy change, because we're subtracting, eventually has to match. So when you multiply Kelvin by kilojoules per Kelvin, the Kelvins cancel and we're left with kilojoules. So again, if you like dimensional analysis as a strategy, it will work here. Okay, so what we're going to do, there is, this can be a lot trickier than what we're going to do this year, okay? So there are conditions where the temperature is going to have a humongous impact on whether something is going to be spontaneous or not, or favorable or not. So what we're going to do is, because we're going to stick with the standard values in grade 12 and we're going to stick with 25 degrees Celsius or 298 Kelvin, then we're not really going to stress about the ones that are weird, okay? So the next slide, if you happen to have the note printed off, has a chart in it. We'll talk about really what you need to focus on, okay? So because you're subtracting, if you have an endothermic reaction that has a small delta H, but has a big increase in entropy, then you can still get the net change to be spontaneous. So there are changes that will be spontaneous. They will spontaneously absorb energy, sort of like what you guys saw with the solid that will absorb energy and make a solution colder, your calorimeter solution colder. You didn't do anything to it, right? You didn't change the temperature of the water. You just put them together. So there are situations like that. But still, what we're going to focus on is the top bullet point here, okay? And then even if a spontaneous reaction is occurring, it doesn't really tell us about how fast the reaction is. So that's another thing about reactions we have to consider, which we'll do in the next unit. So somebody asked me the other day, I can't remember if it was this class, is the next unit sort of an extension of this? And it really is. They complement each other, okay? So what I want you to do is highlight this. Okay, so that would be these two spots in our table here. Spontaneous at all temperatures or not spontaneous at all temperatures. So those are the ones that in grade 12, that's what we'll focus on. So reaction with a negative delta H, which is XO, and an increase in entropy. So you're getting heat energy released, and you're getting an increase in randomness, then that makes sense that the delta G is negative. Yes, that's more spontaneous. Reactions with a positive delta H, which is endo, which you would have before today thought of, oh yeah, okay, that means that it's not spontaneous, it has to absorb energy. But there are cases where, like our solid, if you have started with a solid and made ions, then entropy is increasing. But if you just consider the delta H value, you would have maybe thought of it as not favored because energy had to be absorbed. So those ones are a little bit trickier to analyze. In fact, to be honest, this is very nasty. What I want you to do is take a look at a situation and say whether the entropy increases or not. And there's plenty of practice to do that. And you'll see that looking at what's happening with the change of state or counting the moles of gas, it's not that hard to do. And then doing the calculation, which means you don't have to do the theoretical part of it at all. You can look at whether delta G is positive or negative. That's it. So if you want, you can those are the two cases we highlighted above. Okay? So when you have any matter on Earth that is above absolute zero, which, as you know from grade 11, is the conditions for life on Earth. And we talked about in grade 11, actually maybe even grade 9, if your teacher talked about the particle theory, matter always has to be moving, even if it's just vibrating. So this is the second law of thermodynamics, that the entropy is always going to be increasing if it can. Okay, so there's always going to be a movement towards entropy. So when we do the calculation, then we're going to use standard values, which are these two are on page 799 to, oh, it says it right there, 799 to 800. The only annoying thing about this is the delta S values are joules. Okay, so you're going to have to divide by 1,000 to get kilojoules. So because we're going to subtract, your units have to match. Okay. And what you'll see is when you look at those numbers, the randomness and disorder is not as big of a deal as the delta H value, which does make sense. That's why we focus more on enthalpy change and all different kinds of ways of measuring enthalpy. That has a bigger impact on Gibbs free energy, or the energy available in a reaction to do work. But it's still there. We still have to consider it. And then we're always, actually, don't even highlight the 25. Going to use 298 Kelvin. So when you go to do the homework number 11, you might think, wait a minute, there's no temperature given, because these are standard values. We're always going to use standard temperature, okay? Which again, we did talk about that in grade 11 in the gases unit, but you are reminded here too. So once you've got that down or you're ready to go, if somebody has a textbook, the numbers that you need to do the question, the example we're going to do, are on 799. So the same thing as Monday, it's listed alphabetically. What you can do to save yourself time, because we're going to have to do a calculation for delta H, and then we're going to have to do this calculation for S. So the columns are right beside each other, so you can look up the values at the same time and write them down like we did underneath the reaction. And even though Monday's example was the combustion of methane, and I made you write out the reaction, it'll be more likely that you will actually get the reaction, because again, now the states of the substances really matters. Okay? And that's harder to predict for weird things like, well, we're going to do ethene, right, to ethane. Maybe you've never experienced, you don't know what that is. So it's sort of beyond what we need to do in thermochemistry. I need you to show me that you know how to use this formula. Okay, so calculate the standard Gibbs free energy for the following reaction and interpret the result. Use page 799. Again, if there is a weird value, then it would be given to you in the question. So what we did on Monday was wrote the numbers underneath the reaction, so you can do that again. It's up to you. And like I said, if you would like a shortcut, then you can do both at the same time. Okay, so the reactant is ethene, so C2H4 gas. So it has a positive delta H value. And a positive entropy value. And then again, it does say in the heading, so unfortunately, at first you might be like, wow, this number's a lot bigger than this, but it's actually a lot smaller. So this is actually joules per mole Kelvin, which is, you don't need to memorize that, okay? It's up here in the chart. So eventually, we are going to have to do the conversion to kilojoules. Now, you can do the delta S formula and do one conversion to kilojoules. You can do it now, but you're going to have to change 3 of them, so it's up to you, okay? Of course, this is the elemental form, so its value is 0. If you tried to look it up, it wouldn't be there, okay? So again, it's the elemental form, it's diatomic. I've given you the delta S value. Which makes sense. It doesn't appear in the chart, so I have to give it to you. And then C2H6, so be careful, read the subscripts. The delta F value is negative. Okay, so when you go to do this calculation, just like Monday, you can decide I'm going to show units in my calculations. I'm going to do dimensional analysis, or you can just know what your answer is going to be. If you did the homework from 5.5, you'll know that finding the delta H for the reaction using the formation values, there's no trick to it. Okay, so again, this part of it itself would be out of like 2. Doing the delta S is very similar. Out of 2, if probably I would give you an extra mark because we have to convert it to kilojoules. But those 2 things itself are not very tricky. Just look up the values, or I probably on the test will give it to you in the question. And then you just have to make sure you do products minus reactants for both of them, which is good. Actually, so isn't it wonderful? All the coefficients are 1, but I'm going to show, again, because I want to do dimensional analysis, I'll put in all my work, okay? So this is the product, C2H6. C2H4 is the reactant. And then 0 does nothing. Okay, the moles cancel. So you're going to be left with kilojoules. So really, the math we're doing is negative 83.8 minus positive 52.5. Yeah. So now we have to do the relationship from today, which is virtually identical, right? Just the S values or the entropy values instead. Sorry. All right, so moles cancel. So again, decide what your strategy is going to be. I have a good relationship with my calculator. I can do 229.1 minus bracket 219.3 plus 130.6. But you have to do the adding before you subtract. And you should get negative 120.8. But again, this is joules. Which does not match this. Oh, not moles, sorry. Which does not match this, okay? So every time you do S, you either have to change the kilojoules here or change your answer once. So that's usually easier. And once you change it to K, you might be like, "Yo, Miss Todd, that's tiny, really?" Yes, I know that it is tiny, and that's why we focus so much on heat transfer, enthalpy change, but it's not nothing. Okay, so and if there is a reaction with a greater increase in entropy, then and a greater absorption of energy, then you will have more free energy. So it's the reactions that are weird that actually using Gibbs free energy is a little bit better to decide whether it's favorable or not. Okay, so we're going to do the delta G calculation. And then it says to interpret the result. What that means is you just need to say if it's spontaneous or not. And remember, we're always going to use 298 Kelvin. sorry that there's not enough room. Okay, so the Kelvins cancel. And now we have kj, kj, so we can subtract. Again, you can do this in one step in your calculator or not. So the delta G value is negative, which is spontaneous. So you can see that that was quite a bit of looking up values, calculations. I obviously can't give you a ton of these. And number 11, the second, the B is oh. Nope, I just can't read my own writing. Thank you. It's not negative. Thank you. Let me just double check, but no, it is negative. But maybe I didn't put the negative on the other side. Yeah, sorry. This is negative. I just forgot the negative over here. Yes, but that's right. There we go. Sorry. So 11B, the answer, if you look up your math answers in the back of the book, the answer is wrong. So check out the solutions. And it's you in the real world, we want in a practical way, most of the reactions, even if they're endothermic, we would like them to be spontaneous. So there's a very good chance that your answer will be spontaneous because that makes a lot more sense. So I encourage you to try some of the theoretical ones because it's actually more straightforward than it seems. You're really just looking for, does it become more disordered or does it become more organized? And then if you're given the actual numbers, if it's delta G is negative, it's spontaneous, delta G is positive, it's not spontaneous.